Okay, so now we're going to move on to frequency curves and relative frequency curves. So we're going to be doing this only with quantitative data, but not qualitative data, because with quantitative data we can also graph using lines rather than bars. And the types of line graphs that we can be using, or at least two kinds, are frequency curves, also sometimes called frequency polygons, and relative frequency curves. Now, we'd already shown some histograms, these ones with the bars touch for quantitative data, before, and I want to show you what it looks like to have a frequency curve and a relative frequency curve just overlaid on top of a histogram. So this is from the last little section of lecture. As you can see, there's a frequency curve that's overlaid on top of these bars, and they basically hit the midpoints where the bars hit on a histogram. So you can now see the frequency curve and similarly the relative frequency curve. So they're really just following along the histogram. But usually you construct a frequency curve directly from a table without the histogram. So let's show what that would look like. So you have the table with the frequency and relative frequency in the same data, and what you do is you plot the frequency curve. Now you always have to anchor both sides of the curve. So I'll start with plotting from the origin here. And then we can see for the 80 to 84 scores, we had 5 people score there. And then for 85 to 89, 4, 90 to 94, 6, and 95 to 99, 5. And then we go ahead and anchor it to the x-axis again. And that creates the frequency curve or frequency polygon. Now let's do the same thing for the relative frequency curve. Now we've instead, same data, we've plotted relative frequency, the percent, on the y-axis, but everything's the same. We still anchor our curve. And then we plot the relative frequency. So we go to 25% for 80 to 84, 20 to 85 to 89, 30 for 90 to 94, and 25 for 95 to 99. And then we go ahead and anchor it back on the x-axis. So that's the basics of those frequency curves. Now, it's often useful to construct 2 or more frequency curves or relative frequency curves on the same axis, on the same graph, which lets you easily compare 2 different sets of data. So, for example, we have scores on an exam for Class A and Class B, and here I'm plotting the relative frequency. So, now let's draw 2 curves on the same set of axes. Now here on the x-axis we have the score with the interval class ranges there, and then we have on the y-axis relative frequency. Now let's start with Class A. So we go ahead and we anchor the curve, and then we plot the relative frequency. 4% for 80 to 84, 33% for 85 to 89, 42 for 90 to 94, 21 for 95 to 99, and then go ahead and anchor it on the other side. We've plotted Class A in blue, and now let's plot Class B. Same thing. If you're going to do this yourself, it's good to have either a hashed line and a solid line, or 2 different colors. That's totally fine. That's even better. So here's Class B. We start at the origin, where we have 35% of this students scoring between 80 and 84, 50 between 85 and 89, 10 between 90 and 94, and 5 between 95 and 99. And then we go ahead and anchor it back on the x-axis. So here we've used relative frequency. Could we do the same thing with frequency? Sure, but that only makes sense if there's approximately equal number of observations in both of the groups that you want to plot. Otherwise, it can be very misleading. So it's usually better to do this with relative frequency. And we've used 2 different types of lines, 2 different kinds, and we've indicated which class goes with which line. See, I have Class A in the little blue circle and Class B marked with the red circle, so we know which ones are which. Now let's interpret this data. Which class did better on this particular exam? No, it's actually clearly Class A, right? Their whole distribution is shifted toward the higher end of the scores. They have more scores in the 90 to 94, 95 to 99 range. Don't be misled, because Class B, even though it has that higher point way up there, that was down at 85 to 89%. So most of Class A was scoring in the higher range, while most of Class B was scoring in the lower range. So what you're seeing is these kind of shapes of these distributions here. And different sets of data can yield different distributions with very different shapes. Now, some of them seem to turn up over and over again, and they get special names. So let me show you some of these common ones. So we have a symmetric distribution. The x-axis here is just some random numbers. They could be anything. Where the tails here are symmetric. So the tails on the end are equally large on either side. Then we have asymmetric distributions. And these are called skewed distributions. So we have negative skewed distributions where the tail is toward the lower numbers, like you see on the left. So this long tail is happening at the lower end of the x-axis. Where there's positively skewed distributions, where the tail happens on the higher end of the x-axis. We're going to come across this concept of skewness again later in the course, because it turns out it's going to be important for a lot of different things. But just so that you're familiar with these distribution shapes now, you can kind of see we have these symmetric and asymmetric ones, and the asymmetric ones can be skewed in negative or positive directions. Okay. So far we've looked at graphs for frequency distributions and relative frequency distributions. But earlier we talked about two other types of distributions. There's the cumulative frequency distribution and the cumulative relative frequency distribution, CF and C% respectively. And these can be graphed as well. But these graphs look quite different from the graphs we've made so far. So let's take a look at a data set. So again, we're just going to use class scores since we've been doing that the whole time. And we have the frequency, relative frequency, cumulative frequency, and cumulative relative frequency. And we have an n of 24. So let's make a graph for cumulative frequency. So what we have on the y-axis is cumulative frequency, CF, and on the x-axis we have the exam scores. And what I've done is designated each point on the x-axis here with the upper limit of the class, so 84, 89, 94, 99. Technically, you should use the true upper limit, so 84.5, 89.5, but using the regular, the apparent upper limits is good enough for most purposes. So you should just go ahead and use the apparent limits of the class, the upper limits of the class. All right, so what we're going to need to do is we're going to anchor the curve to the x-axis here at the origin. And then we go up to the percent of scores that fall in the, the number of scores that fall in the 80 to 84 class, which is 1, so you don't really go up much. Then we have 9 scores that fall from the 85 to 89 range and below. We have 19 scores that fall from 90 to 94 and below, and 24. All of them fall below 99, score of 99. Now make sure you go back to the other slide, maybe jot down the cumulative frequency there so you can map this on to this actual data here. So what you can see is that we've anchored the curve to the x-axis on the left, the lower end, but we don't anchor the curve to the x-axis on the right because it always needs to end at the true number of observations we had, which was 24. Now, we're going to make a graph for cumulative relative frequency as well. Exactly the same idea. X-axis is exactly the same, but here the y-axis changes. Now we use C% or cumulative relative frequency instead of CF. Now, note, you always want to end at 100% here. It can't go above that. And the graphs for CF and C% are going to have the same general shape. So now, if you go back to that data set you had a few slides ago, you can rewind and write it down. You can see what we're doing here. We anchor it on that x-axis at the origin, and then we move up to 4% for 80 to 84. 38% of scores are below 89. 79% of scores are below 94. And 100% of scores are 99 or below. So you can see we don't anchor that graph and it has to end at 100% because all the scores are at that level or below. All right. So now I'm going to show you an example of a graph. And tell me what's wrong with it. It's a cumulative relative frequency graph. So why would this one be wrong? A cumulative relative frequency graph can never dip. Remember, we're always adding. It can be flat if you have 0 observations at a particular interval class, but it can never dip down. So if your cumulative relative frequency graph dips, just as if your cumulative frequency graph dips, something's gone wrong. It can be flat, but it cannot dip. So this dip at 94 is wrong. Just keep that in mind as you're going to create these on your own. And finally, note that with a cumulative relative frequency graph, we can read off percentiles from the graph itself. So if we look at a score of 89, we can see that that's about at the 40th percentile. So if you have this cumulative relative frequency graph, you also have a percentile graph. All right, so to summarize, if you have qualitative data, you can use bar graphs. If you have quantitative data, you can use histograms, which are like bar graphs except the bars touch. And you can also use various types of curves. So we have the cumulative frequency, relative frequency, frequency, and cumulative relative frequency. And these curves can have basically a symmetrical distribution, which is also sometimes called the normal distribution. We'll talk about that later, as well as positively and negatively skewed curves. There's lots of conventions involved in graphing, but the purpose is to present data in a clear way. So it's also important to look for misleading graphs. And graphs may be constructed to support a particular point of view, which gives credibility to the popular saying, numbers don't lie, but statisticians do. So let's take a look at this graph of number of major felonies in 2007, 2008, and 2009 in, let's say, Boston. So take a look at this graph to the left. What we see is a large increase in the number of major felonies or major violent crimes over those 3 years. Now look at the graph to the right, and there's really just small increases, barely even noticeable increases over those same 3 years. So maybe the data were taken from different cities, or maybe they were taken different types of crimes that were being considered. But no, it's actually the same data. It's just different y-axes. So to make the increase in major felonies or number of violent crimes not look as bad, they changed the frequency on the y-axis from 215 to 230 to a much wider range from 200 to 600, which then shrinks that graph and skews the truth. So always beware, look at the x-axis, look at the y-axis, and see whether these whether data are being presented in an honest manner. Okay, so that's the very end of all of the lectures for the day. So make sure that you, if you want to get that extra credit point, give an honest effort at the last 4 review problems in the book, 2.14 to 2.17, the 3 parts each, and pass those in either through email if you scan them, or if you've done them online, if you've done them on a word processing program or something like that. Or you can just bring them in if you've done them by hand and pass them in at the beginning of class on next Tuesday, September 11th, and you'll get those points. All right, thanks so much for your patience with this week, and I will see you on Tuesday. Bye.